Welcome to the GlobalFoundries technical webinar, Analog Design Workshop for 22FDX, 22nm FD-SOI Technology. Hi, my name is Sean O'Kane from ChipEstimate.com, and we are pleased to introduce the speakers, Don Blackwell and Timothy S. Miller, both senior members of the technical staff at GlobalFoundries. Please note that this detailed workshop is presented in two parts. The first part, presented by Don Blackwell, focuses on analog design, and the second part, presented by Timothy Miller, focuses on analog layout. So right now, let's join Don to learn about 22nm FD-SOI analog design.
This is the analog design workshop for the GlobalFoundries 22nm FD-SOI process as it relates to analog design. This presentation will be in two parts. First part will focus on design, and part two will focus on analog best practices for layout. In the first part, we will focus on the native device capabilities, which means no backgate bias applied. And in the second part, we'll dive into some of the details of the applications of backgate biasing. This is to provide a guideline of analog best practices to harness the full capability of the 22FDX process offered by GlobalFoundries. Also to provide an overview of several FD-SOI characteristics, highlight some of the advantages for analog circuits, and to provide best practice outlines for design and for layout. Designing an FD-SOI is quite similar to designing in bulk, except you have superior substrate isolation. The FET conducting channel is isolated from the well or the substrate by a thin insulating layer of buried oxide known as box. This allows a complete control of the channel and lowers the junction drain source capacitance. It also allows the threshold voltage of the device to be manipulated via the backgate. There are several different types of backgate control we offer. NMOS in N-well, which we call flip well, PMOS in P-well, which is also a flip well. Both of these will use the backgate in what's called a forward backgate bias to lower the threshold voltage. An example would be SLVT NFET devices and SLVT PFET devices. We also have NMOS in P-well and PMOS in N-well, which are conventional well constructions. These are similar to what you would see in bulk, where NMOS devices sit in P-wells and PMOS devices sit in N-wells. In this case, the backgate bias is applied in a reverse direction to lower the leakage of the device for low power applications. With no dopants in the channel, we get enhanced mobility, less sensitivity to layout dependent effects such as length of diffusion, OSC, well proximity effects, etc. And it offers superior device matching. With fewer source drain junction diodes, 22FDX, far fewer latch-up issues. Here we see a basic cross-section of the device as compared to bulk. It will offer lower leakage than bulk, has lower doping effort, so less variation across the chip, and it offers body biasing capability through the back gate. On the right-hand side, you'll see a thin green layer. This is the buried oxide layer, or the box, that isolates the transistor on top from the well or the back gate below. When we compare conventional to flip well devices, you will notice the difference between the device on the left and the device on the right is the position of the N-well and the P-well. On the left-hand side, we have an NMOS device over a P-well and a PMOS device over an N-well. These are conventional constructions, and except for the thin green oxide layer, very similar to what you would see in bulk. On the right-hand side, we see a flip well construction. This is peculiar to 22FDX. You'll see an N-channel device sitting on an N-well and a P-channel device sitting on a P-well. The thin green oxide layer in between the transistors and the wells prevents any forward biasing from taking place between the drain sources and the wells. 22FDX offers improved electrostatics and lower DIBL compared to bulk. All of the activity in the channel is restricted to the narrow region on the right-hand side between the drain and the source and above the box. The leakage paths that would normally run deeper into the bulk do not exist. So this improves electrostatics, improves short channel effects, gives you higher GM, and lowers GS. In general, you would expect to see a reduction in mismatch due to the undoped channels and no halo implants. And we're seeing a greater than a 30% improvement in mismatch reduction. 22FDX offers comparable current and GM over IDS to the highest performing 28 nanometer bulk, and also lower GDS. FT is comparable to 28 nanometer bulk results, but 22FDX does offer a higher intrinsic voltage gain than bulk, and the planar structure allows for a lower RSD and R gate. This shows a Pelgrom plot for Vtsat mismatch. On the horizontal axis is 1 over square root of the area. The vertical axis is a standard deviation of delta Vtsat. The Pelgrom coefficient in the equation on the bottom is A, and it is basically the slope of this line. In general, the shallower the slope, the better. What we're seeing in the diagram is that the larger devices have a better Pelgrom coefficient, or less delta Vtsat, and you're seeing also that the larger the area, the lower the variation, which is expected. Here we compare 22FDX to 28 HKMG. In the top, we compare the Pelgrom coefficients of a PFET and NFET between these two processes, and we find that 22FDX comes out with a superior NFET Pelgrom coefficient and a superior PFET Pelgrom coefficient, which means lower numbers in both cases. The charts on the bottom are a comparison between 22FDX and 40LP. On the left-hand side, the two charts are the Pelgrom coefficients for Vtsat and for IDSat. On the right-hand side, we compare the standard deviation of Vtsat, and you see the N-channel device has a 44% improvement, P-channel device has an 18% improvement going to 22FDX. On the lower right-hand side, standard deviation of IDSat shows 33 and 8% improvement respectively. In all these cases, we're using minimum channel length devices. This shows the intrinsic voltage gain and GM efficiency, 28 HKMG versus 22FDX. On the left-hand side is the self-gain. 22FDX is the orange curve on the top, and it shows a higher self-gain than a comparable 28 HKMG. On the right-hand side, the orange curve is 22 FD-SOI compared to 28 HKMG, and you'll see that the curves are coincident except for very low VGS, where 22FDX shows superior GM efficiency. Here we compare self-gain versus GM over I over a variety of different channel lengths. On the very bottom, the blue line at the bottom is 28 nanometer. The curves encircled above are 22 FD-SOI, and all these measurements are taken at a gain efficiency of about 15. The longer the channel length, you'll see the higher the self-gain, as expected. And here we measure the FT versus GM over IDS, again measured at a gain efficiency of around 15, as in the previous chart. And this shows the FT as a function of channel length. And as expected, the shorter the channel length, the higher the FT. When we compare 22FDX to 40LP, for the same area, 22FDX is showing a superior GM over GDS, and also GM over IDS. In this case, you'll note the GM is 5.79 milli for 22FDX, and for 40LP it's close to 2 milli. So we see a dramatic improvement in these parameters for the same area. In this slide we compare the FT of 22FDX versus 28 nanometer bulk. The two yellow boxes compare small devices, 1 micron W over minimum channel length for both 22 and 28. The green boxes compare larger devices, F of T, 10 micron W over minimum channel length for both 22 and 28. You'll notice that 22FDX has a higher F of T for both a 1 micron and a 10 micron device. One of the improvements that we get with 22FD-SOI is we eliminate the drain and source reverse bias diodes that are associated with the bulk. This process has a thin box layer that isolates the drain and the source from the bulk, and in doing so we remove that voltage-dependent capacitance between the drain and source and the bulk. Here we see the source capacitance of dP and dm on the left-hand side has been basically removed or minimized because we no longer have these reverse bias diodes. This improves the linearity of the device by removing this impedance to ground. In this slide we reduce the propagation delay of a ring oscillator by using an ELVT PFET device in the ring oscillator instead of an SLVT PFET device. Normally in ring oscillators, the N channel and the P channel device will be of the same type. SLVT PFET combined with SLVT NFET, etc. But here we replace the PFET with an ELVT PFET device to increase the speed and reduce the delay. The ELVT PFET has an Vtsat of about a milliamp per micron of W and 20 nanometers, about 25% more than the SLVT PFET. So we get reduced W for the same drive and a lower C load. It also reduces the footprint of the P-channel device, making for a smaller ring oscillator and a faster one. So custom logic is possible. You can mix and match devices. And in this instance, where we wanted extreme speed, we use the ELVT PFET device instead of the SLVT. 22FDX offers scalable models for several versions of AP-MOM caps and MOM caps. Depending upon the voltage required, 2.5, 3.3, on up to 10 volts, the spacing and the width of the various metal layers will change, as you see on the bottom. The spacing will increase as the voltage requirement increases. This chart shows the AP-MOM and MOM capacitor local mismatch, primarily as a function of area and number of metal layers. The best matching is achieved when these capacitors use all 6 metal layers, and the mismatch coefficient is approximately 1.5%. As the number of metal layers are reduced, the mismatch will increase, so with 2 metal layers we get up to 4% mismatch. In this process, AP-MOM needs to have at least 3 metal layers. The chart on the right shows the slopes of these curves, the mismatch coefficient, and you will see that as the area increases, the mismatch improves, as we would expect. Also, as the number of metal layers increases, the mismatch also improves. In the next section, we'd like to go over some of the uses of the backgate. The backgate allows us to manipulate the VT of the device independently from the front gate. On the left-hand side, we see a cross-section of a conventional bulk NMOS device, and you'll see the drain and the source diodes. On the right-hand side, you see an FD-SOI device where the difference, the primary difference that you'll see is the green BOX or buried oxide layer, isolating the drain and the source from the underlying P well. On the lower left, the diagram is a cross-section of either a regular well or a flip well device, depending upon the device sitting on top of the N well. If we put a PMOS device on top, a PMOS over an N well is a conventional style structure. We refer to that as regular well. However, we can put an NMOS device on top of the N well, and we refer to that as flipped well. As an example would be SLVT NFET. The diode between S3T3, which is a deep N well, or the P substrate, needs to be taken into account so that an accidental forward biasing does not happen. Note that the P sub or ground will be at ground, so the deep N well cannot be taken below ground. On the right hand side, we have a triple well device. In this case, we add a P well. Depending upon whether or not the device above the P well is a PMOS or an NMOS device, it could be either a regular well device or a flip well device. We also have an additional diode between the P well and the deep N well. And we have to take precautions to make sure that that diode does not get forward biased between P well and deep N well. And also we have to be cautious that we do not forward bias the diode between the deep N well and the P sub. Forward body bias uses flip well devices. In this case, we see examples of an N well with an N channel device and a P channel device sitting over a P well. For forward body bias, the N well cannot go below ground for the N channel device. It ranges from 0 to plus 2 volts, and the forward body bias for the P channel device ranges from 0 to minus 2 volts. In actuality, this 2 volt limit is not a hard and fast limit. The back bias can exceed these voltages, but the modeling is only accurate at this point up to the 2 volt limit. Beyond that, the model begins to become a little bit less accurate. Forward body bias works with the gate voltage, meaning that it moves in the same direction as the gate. So as the N channel gate is raised to turn the device on, the back gate bias raised would also turn the device on even harder. So more forward body bias means more performance, and it lowers the VT of the devices. This is the cross-section in more detail. The diodes that we mentioned before that are associated with the substrates and the wells are shown here again. On the left-hand side, we see the diode between the N well and the substrate, and below that is a schematic diagram of our models that take this diode into account. This is a 5-terminal transistor model. We recommend that this be used so that accidental forward biasing of this diode is much less likely. On the right hand side, we have a 6-terminal model to take into account both diodes associated with the P well and the T3 to bulk. Again, these extra terminals take into account the diodes and reduce possibility of accidentally forward biasing these diodes during simulation. Reverse body bias uses a construction very similar to bulk. N-channel devices sitting over P wells and P-channel devices sitting over N wells. The difference between this and bulk again is the thin oxide layer between the devices and the underlying wells. For the N-channel device, the back gate cannot go below 0 volts in the reverse body bias case. It ranges from 0 to plus 2 volts. For the P-channel device, the back gate is restricted to 0 volts to minus 2 volts. Once again, these voltage limits, plus and minus 2, are not hard and fast. They represent more characterization limits than breakdown limits. The models are accurate between 0 and plus and minus 2 volts, and the models become less accurate as you exceed these voltages. In reality, these voltages can go as high as the breakdown voltage of the diode. Reverse body bias works against the forward gate voltage, and it effectively increases VT. So reverse body bias is used to reduce leakage and to save power. Here we see a cross-section of the conventional well FETs, a conventional NMOS device on the left and a conventional PMOS device on the right. As with the forward body bias situation, there are diodes between the various wells and the bulk, and the models underneath show the additional terminals added to the schematic models to take these diodes into account. Again, these extra terminals are intended to assist the designer in avoiding a forward biased condition during simulations. The purpose of using 5 and 6 terminal devices is to avoid forward biasing the underlying well diodes. When simulating with these devices, you'll notice on the right hand side there's a field in a dotted square. This takes into account the perimeter and area of the underlying diodes. So if several devices share a common well, it's possible to go into this area and modify the associated well area and perimeter to take into account the additional capacitances of this underlying well. For RF networks, there are some additional components added. In particular, the well resistances are modeled. On the top we see an NMOS flipped well or a PMOS conventional well device with a single diode between the deep N well and the P substrate, and several associated resistors with the N well. On the bottom is a PMOS flip well or an NMOS conventional well, which has 2 diodes, one diode between P well and the deep N well, and another between the deep N well and the substrate. Again, substrate and N well resistances have been added to these models to take into account the frequency response of the wells and associated substrate. The RF models are not scalable. These are fixed structures. So when using an RF model such as this, you would simply deploy the P cell directly. W's and L's would not be scaled. It would simply be taken and placed and used as is. Here we measure the coupling from one N well tap to another with and without an underlying deep N well. On the right hand side, what we see is a family of curves that show what this coupling would be as a function of distance: 10 micron, 20 microns, and 40 microns spacing. So as expected, the greater the spacing, the better the isolation. And also, we find that when we remove the deep N well, we get better isolation, which again is not unexpected. Here we measure the coupling between an N well tap and a P well tap. In this case, a reverse bias diode exists between the P well tap and the underlying N well. Again, as the distance increases, we see isolation is improved, which is not unexpected. And if we continue and add a deep N well to this structure, again we find that as distance increases, isolation improves, but the isolation is not as good as without the deep N well. Here we measure the resistance between one N well tap and another. We measure the resistance between 2 N well taps in the presence of an underlying deep N well. As expected, as the separation between the taps gets larger, the resistance between the 2 taps also increases. On the bottom we repeat the experiment, but without the deep N well. Still, as the distance between the taps increases, so does the resistance. But overall, we see a greater resistance between the 2 N well taps because we no longer have the deep N well underneath. So to increase the resistance between these taps, we would remove the deep N well. In this next section, we'd like to go over some of the techniques employed with backgate biasing on certain selected circuits. What are the advantages of backgate biasing? You can trade off power and area reduction for the same performance target. It can be used for trimming, gain, bandwidth, delay, etc. You can employ forward back biasing to lower the threshold of the device and increase the GM. You can employ reverse backgate biasing to save power and reduce leakage. So this provides a trade-off between performance, power, and area. Now it's possible to have both forward and reverse backgate bias devices on the same chip. It's just that you need to be careful to select which is which when you're designing your circuit. Forward backgate bias or flip well device is not the same as a conventional well device, and you cannot simply change the voltage to turn one into the other. They are dedicated structures when you build them. It's either a forward backgate device or a reverse backgate device, so this has to be established during the design phase. This shows some of the possibilities that are available using backgate. Device parameters such as current, resistance, and DC operating point adjustment and mismatch can be adjusted using either forward or reverse backgate applications. And this shows examples of some of the circuit benefits and various circuits that are associated with these parameters. For example, in the case of a switch, you can control the R on or the R off of the switch for either high or low resistance, depending which parameter is important. And any circuits using such switches like capacitor arrays, switch capacitor filters, mixers, etc. would benefit from this. This shows a fairly typical single gain stage driven by a constant bias current, and when this is built with extremely small channel lengths, minimum size devices, something a little unusual happens. We notice that the bandwidth increases as forward backgate bias is applied, even though the gain and the phase margin remain relatively flat. This is not normally how an op-amp would work. This would not happen because the bias current is constant. With a combination of extremely short channel lengths, especially in the N-channel devices, and forward backgate bias applied, we do notice this effect. Op-amps are not normally constructed with minimum channel length devices, and if this were constructed with the more conventional channel length devices of 2 or 3 times minimum, this effect would not be seen. It's only when you get down into very small channel lengths that we observe this effect. While this may not be suitable for a signal type amplifier used in a filter, it might be very useful for amplifiers used in regulators and static situations. If we reduce the W's of all these devices by 50%, the trend continues. The gain and the phase margin remain relatively flat, and the bandwidth continues to increase. Again, if the channel lengths are restored to a more conventional length, 2 or 3 times minimum, this effect is not observed. It seems to be an artifact of very small channel lengths combined with forward backgate biasing. In the previous example, forward backgate biasing was plus and minus 2 volts, but that may not always be available. So if the only voltage available to you is the supply voltage of 800 millivolts, you can still apply forward backgate biasing, but it'll be restricted to, in this case, the 800 millivolts supply. The bandwidth, again, is still observed to increase while the gain and the phase remain relatively flat. Again, this is for a minimum channel length structure. Predominantly, it's the N-channel devices in this case that are responsible for this increase in bandwidth. Strictly speaking, the P-channel devices here are not forward backgate biased, but they're actually reversed backgate biased because the voltages applied to the backgate of the PFET devices are greater than 0. This is an example of a switch where we use forward backgate biasing to reduce the on resistance. As you increase the forward backgate bias, not only does the on resistance get smaller, but also the variation in on resistance gets smaller. In this case, R on max drops from 480 ohms to 250 ohms. And the variation in R on changes from a range of 250 ohms to a range of only 60 ohms. So it provides much flatter on resistance, as well as a lower on resistance. Conversely, if we apply reverse backgate biasing to a switch, we can increase the off resistance of the switch dramatically. Here, R off min increases from 2 megohms to 50 megohms, but R off max goes all the way up to 430 megohms, albeit with a greater variation in R off. Note that both devices must be conventional well type to allow for reverse back biasing. In the previous example, forward and reverse backgate biasing went as high as plus and minus 2 volts. Those voltages may not be available. Sometimes there may not be a charge pump or an external voltage available to supply the forward or reverse backgate biasing voltages, and you're restricted to operating just with voltages that are available from the supply. In this case, we simply hook the front gates and the back gates together for each of these devices. And even with this simple configuration, we notice that we get an improvement in R on, where we reduce R on max from 460 ohms to 380 ohms. So additional backgate control will permit a reduction in the threshold voltage. And the switches benefit from a smaller R on per W and R on C. So As R on per W gets smaller, the switches get smaller, the layout gets smaller, which means smaller parasitics, and the switches get even smaller still. In this example, we used forward backgate biasing to reduce the area of an op-amp that was fairly area intensive. The area in orange was selected for reduction, with no forward back bias applied on the left, and with a forward back bias of minus 1.2 volts applied to the PFETs on the right, we see an area reduction of approximately 30%, and the performance remains similar. The area shown on the left was this op-amp with no forward back bias applied. The layout on the right shows the same op-amp with a minus 1.2 volts back bias applied. In this example, we compare the power supply rejection ratio of two comparators, Comp1 and Comp5. Comp1 on the left uses a conventional type backgate connections where the P-channel backgates go to VDD and the N-channel backgates go to VSS. On the right, Comp5 uses a different type of backgate connection where the backgates in general connect to the front gates. The exception is device P2, where its backgate connects to the gates of P1 and P0. The intent here is to connect the backgates to something other than the supplies and decouple the backgates from any noise from the supplies. What we see is that when we use this modified backgate connection is we gain an 8 dB improvement in power supply rejection ratio. If all this supply rejection is not needed, the performance can be traded for an area reduction in these devices or for lower power. Backgate biasing can be used for correcting comparator offsets. In a conventional type of structure, this means adding additional devices to the inputs or signal path, increases the loading, and adds additional devices. But in 22FDX, we have access to the backgates of these input devices. So instead of applying offset correction to the front gates of the input, we would apply offset correction to the back gates of the input devices. A calibration scheme can be set up where the output is monitored and the correction signal is returned to the back gates of the input devices to remove the offset. This shows two different linear regulators, one with an NMOS output and one with a PMOS output. In both cases, back gate bias is applied to the PMOS current mirrors to lower the VT and to bring the VDD down to save power and to increase headroom. The output devices can then be manipulated through the backgate to optimize the operating point of each of these linear regulators. In an all-digital PLL, a large percentage of the power is consumed by the oscillator. So any savings in power in that oscillator is going to be valuable. In this particular example, we saw 85% of the power being consumed by the DCO core. Backgate bias was applied to the P-channel devices as well as to the N-channel devices in the oscillator. In this case, forward backgate bias to both, and it reduced the headroom by 200 millivolts. So with a supply of 1.5 volts, reducing the supply to 1.3 volts is approximately a 13% power savings. This is also going to reduce the dynamic range of the oscillator, and it will increase the phase noise. So if there is sufficient phase noise margin, then it's possible to reduce the power supply and also save some area. If we apply forward backgate biasing to both the N and the P-channel devices, this will reduce the dynamic range of the oscillator and increase the phase noise. But as long as there is a sufficient phase noise budget, 13% can be saved in power by reducing the supply voltage this way. The circuit on the left shows a conventional GM cell as part of a GM-based filter. Above the GM filter, we have a regulator circuit and a variable VREF for tuning. If we apply backgate bias to the GM cell, we can remove the variable VREF and save the headroom. On the right-hand side, we see the supply budget allocated for each block in this circuit. So if we were to remove the VREF and apply the tuning to the GM cell, we see that we can either lower the overall supply voltage or we can increase the headroom on the GM stage for a wider dynamic range. We therefore have a trade-off at that point. If we were to go all the way to the extreme and remove both the VREF and the regulator, we could let the backgate biasing do the work of all of these things, but we would pay a penalty in power supply rejection if we were to remove that regulator. An ADC was designed for a 600 megasample per second sampling rate, and the power was noted as 1.7 milliwatts. This SAR ADC also had a low speed mode that ran at 400 megasamples per second. Again, this was operating with forward backgate biasing, but when the forward backgate biasing was removed, the power dropped from 1.23 milliwatts down to less than a milliwatt. On the right-hand side is a chart of the power spectral density, and what was noted was this PSD did not change between applying forward backgate biasing and removing forward backgate biasing. So it's possible to save power without suffering any performance loss here. A conventional charge pump is shown on the left-hand side, where all the bulks of these devices go to ground. In 22FDX, the back gates of all the devices are hooked up in parallel with the front gates, except for the first stage, where it's driven by an inverter. This means that both sides of the transistor are working, not just one side. The end result is that to achieve the same 4-volt output, only 3 charge pump stages are needed, and we can save 20% in power and 25% in area. Conversely, with the same power and area, a 4-stage pump could deliver a higher output voltage, which would give you 60% more voltage and close to a 30% better power efficiency. So there's that trade-off between power and area. In this example, we apply forward backgate biasing to the cascode pair. In this example of a current mirror, we utilize forward backgate biasing to save on the number of devices used and also save on headroom. As you see, on the left-hand side, we have 6 devices in a swing-enhanced cascode in a conventional type of structure. In the center, we have a resistor in a self-biased swing-enhanced cascode. On the right-hand side is a proposed 22FDX solution where these components have been removed and the backgate biasing has been applied to the cascode devices to do all the work. The backgate bias can be used to calibrate a current steering DAC. In this case, we don't have to manipulate the V-bias node. The backgate can be accessed directly to control individual segments or individual cells for calibration. We can also use the backgate to adjust a mixer, and in this case what we'd like to get rid of is the intermodulation product F2 minus F1. And as we adjust the backgate voltage, we observe that intermodulation product reducing. This is an overall view of the SAR ADC that was mentioned earlier that ran at 600 megasamples per second. This is just a general topology. In this SAR, we used custom logic with EL-VTP FETs to get the high-speed throughput for signal and asynchronous clock loops. Again, when this SAR was run at the lower sampling rate and forward backgate biasing was removed, we suffered no degradation in power spectral density, but we did save a significant amount of power. So backgate biasing can be used to save power when needed or turn it on when performance is required. And this is just a layout of that ADC showing that it occupies about the same area as a typical bond pad. For noise and isolation, we offer a BF moat layer which blocks PO implants and creates a high resistive substrate. This is drawn over critical RF and analog lines to reduce coupling to and from the substrate, and sometimes drawn over inductors to reduce substrate losses and improve the Q. Typically guard rings are used in sensitive analog RF blocks, but sometimes when guard rings cannot be squeezed in, the BF moat ring can be placed around a sensitive block for additional protection. This is a floating ring, basically a thin region of resistance or high resistivity substrate. It is not connected to ground or to a supply. It's not necessary to completely encircle a sensitive block with BF mode. Sometimes it's only necessary to place a bar of it in between the sensitive block and, say, a noisy block, just as a shielding component or additional protection. And once again, this is a floating layer. It's not attached to a ground or to a supply. The back gate has to be considered as a signal connection, and like other signal lines or bias lines, care should be taken to isolate that bias line from high-frequency interconnects. It's best to route the backgate line or bias line perpendicular to other high-frequency interconnects in the chip wherever possible, and if it runs any great distance, you would want to shield it just like any other bias line. If a large number of devices is being controlled by a single back bias generator, one concern is that noise coming in through the front gate of any single device can propagate through that backgate bias line and affect all the other devices connected to that line. So it might be necessary to add decoupling capacitors to this backgate bias to prevent that from happening. This is similar to any other bias line where it needs to be kept quiet. This would be called kickback noise. And when we evaluated this noise with no capacitance and with even a half a picofarad of stabilizing capacitance, we noticed that the noise on the back gate was reduced from 488 millivolts to only 12 millivolts peak to peak. This is noise coming in through the front gate of one device and showing up as ripple on the back gate voltage. So even a small amount of capacitance will render a dramatic improvement in whatever noise is injected into the backgate. This chart simply shows the backgate noise observed as a function of N-well or P-well capacitance from 0.1 to 100 puff. And depending upon the capacitance applied to the backgate bias line, it is possible to reduce the backgate biasing noise to practically nothing. This chart shows 1/f noise variation as a function of backgate bias. The devices that we're using are core devices, 1 micron by 20 nanometer, and what we're seeing is the drain noise and the gate noise. The drain current noise and gate voltage noise both decrease dramatically with the application of forward backgate bias. So what we see is current noise density is reduced by 45% for the NMOS, 20% for the PMOS, and the gate noise, normalized gate noise, is reduced up to 37% for the NMOS and 13% for the PMOS. Since the buried oxide layer of 22FDX is very thin, self-heating effect may not be as significant as in other SOI technologies that use a thicker oxide layer. Note that the self-heating is related to the local power consumption. We do model self-heating. In HSPICE we have a parameter called GSWSHE, same as inspector. This is turned on when we want to evaluate self-heating. By default it is turned off. For general purpose analog circuits operating with low currents of 50 microamps or less, the chart below shows the temperature rise that we've observed. And here we show an EG-LVT PFET device, 9.6 microns W and 150 nanometer length. And even with 50 microamps of ID, we're seeing a temperature rise of less than 0.3 degrees C. One of the effects of simulating with self-heating turned on is longer simulation times. In this case, we ran a DAC with and without self-heating turned on. No significant difference was observed in the I&L simulation results, but the CPU time was dramatically increased. A similar effect was noted with the VCO ring oscillator, with and without self-heating turned on. With self-heating turned on, we saw no real significant difference in the output, but again we noted a dramatic increase in simulation time. In the case of a charge pump, we actually did find one of the stages was affected by self-heating, and we had to go back and correct this. Self-heating being turned on identified the problem. Again, the simulation time is dramatically longer. So, in conclusion, we recommend turning self-heating on at the beginning of a design phase to define basic architecture and to identify any initial problems. But for small incremental changes, turn it off to save simulation time, and don't turn it on again until the final simulation, just to catch any final mistakes or make any design corrections.
Thank you for joining us for Part 1 of the webinar Analog Design Workshop for 22FDX 22nm FD-SOI Technology. If you have any questions, please email them to marketing@globalfoundries.com or contact your local GlobalFoundries office. Also, for more information about FD-SOI, FinFET, ASIC, RF, and other technologies can be found at globalfoundries.com.